Now we've done an example that had the normal strain by itself and then shear strain by itself. Let's take a look at an example that contains both epsilon and gamma, either in the problem statement or what we're trying to find. This is a pretty complicated example, and it's one that would probably max out what we would have in terms of level of difficulty in this class. It's again going to be a rectangular sheet that looks something like this. And we're given a height of 150 millimeters. And the length in the x is actually unknown. We're given, however, this angle of 35 degrees, like so. Along with this data, we're given that epsilon xx, and remember there's really only one subscript that we care about, and that is the normal strain that was originally aligned in the x direction. But officially there are two, but we can think about it as only having one for this class. And that is equal to minus 2,000 microstrain. And we're going to remind ourselves of what that was. We just talked about it. Epsilon yy is equal to is equal to epsilon y, and that is minus 1,500 microstrain. So both the x and the y directions are shrinking. And then gamma xy, and now we better put on some coordinates. That's x, and that's going to be y. Gamma xy, and that has to have two subscripts with it because it's the line elements originally in the x and the y directions. And that's equal to 1250 microradians. Now you could also just say mu, that would be okay, and then it's up to you to realize that that's going to be times 10 to the minus 6th. So we think, what does that mean? That means that this angle, remember that was originally at 90 degrees, is going to be getting smaller because the shear strain is positive. So our thumb and forefingers move in the positive direction. They get closer together without any sort of problem. We are asked then to find the normal strain in this direction that we'll call n. So we are asked to find, it would be either epsilon nn or epsilon n. In other words, the change in length of the diagonal over its original length. Let's kind of sketch that out. That means delta L of the diagonal divided by the original length of the diagonal. So that's what we're asked to find in this particular case. Now, by way of kind of using this as a teaching example, let me shrink this down a little bit, and I'm going to give you kind of a helpful hint. Notice, remember that epsilon, let's just use x in this case. Epsilon, which is the change in the length in the x direction divided by the original length, that means that the change in the length, if I just multiply it up and switch sides, is going to be equal to Lx times epsilon x. So what that means is that the new length in the x direction is equal to the old length plus the new length, so the delta L. So in the x direction, we would have the length of the new in the x direction, I'm just giving that an ad hoc superscript, is the old in the x direction plus the delta L in the x direction. But now notice, delta L in the x has the old length as well. So we would say that L new, and I'm going to drop off those superscripts now, is the old length. Let me just call that Lx. And then we have plus Lx times epsilon x. So the Lx actually factors out, and you get Lx times 1 plus epsilon x. So that is a very useful statement. It says that the new length in any direction is the old length, I'll say L old, times 1 plus epsilon x. So you don't have to commit that one to memory. You can certainly get the result by using just the basic definitions, but that's kind of constructive. And let's see if we can practice it now. So what we would say is that the new length in the x direction, so we'll call that prime. Let's let the new be the prime. So we would say then that Lx in the prime So the new length is going to be the original length, Lx, times 1 plus epsilon x. So that would be the length in the x, which I don't think we've calculated yet, have we? No, we didn't do that. We might want to write then that up here 150 opposite over adjacent over Lx is going to be the tangent of 35 degrees. So that means that Lx, the original one, is going to be 214.22 millimeters. So that means then that we've got the 214.22 repeated times 1 minus, because the strain in the x is negative, minus 2,000 times 10 to the minus 6. So that's 1 plus epsilon, and that strain is negative, so it's shrinking. And that turns out to be 213.794. Incidentally, be very careful you don't chop off significant figures when you're doing strain. So you want to keep at least 5, 6 digits. Keep 5, 6 figures for strain, because a lot of times it won't be until that 4th, 5th, 6th decimal point that you're actually getting some sort of change. And that's going to be in millimeters. Then we do something similar for the y. Ly prime is the original y times 1 plus epsilon y. So that's our 150. And then we have 1, again, it's negative 1500 mu, so minus 1500 times 10 to the minus 6th. So it's shrinking as well, and that turns out to be 149.775. Now again, don't round that up to 150, because if you only kept 3 significant figures, you'd be back at your original length. So don't do that. Don't even do the 4th. We've got 6 here, and we're going to keep track of that. One other item that we need then is the new angle. So remember, we're shrinking the angle down. So we'll call this maybe delta theta. And here, just to be useful, we might want to convert this thing into degrees. So it's going to be 1250 times 10 to the minus 6. That is the strain, and that's just going to be the angle change. So if we multiply that and convert it to degrees, that would be 180 degrees per pi radians. So that would be 0.07162. So the new angle, let's call that maybe theta prime. It was 90, but now we're taking it off. Remember, the angle's getting smaller. So it's going to be 90 minus 0.07162. And that is 89.9284. So what does that look like now? We used to have this, and this, and this. That's the original. But now, let's draw the new one to the side. They're closer together, they're shorter, and they've got a different angle. So this one is 213.794. This one is 149.775. There is our new diagonal length. Let's call that L sub n prime. And then this angle is our theta prime. Now remember, the original length here, we never calculated. That's going to be the square root of the sum of the squares. So we might want to do that. That would be L sub n. So the original length of the diagonal, we would have had to take the square root of, 150 squared plus 214.22 repeated squared, all to the 1/2. And that turns out to be 261.517. Again, we're keeping 6 significant figures, so we've got that value. All right, back to this. This one, if you haven't seen it before, it might be a little bit baffling, because what you really want is the new diagonal length, because you need new minus old divided by old to get the normal strain in the n direction. So you've got this angle that's no longer right triangle, but you've got one opposite side and two adjacents. And so hopefully little alarm bells are going off in your brain because you're thinking law of cosines. So it's not just for torment. We committed that to memory back in the day. So remember what that says. The law of cosines says that if you have something like this, it's normally written as A, B, and C, and then that's your theta. So it's the angle opposite to the C side. So you've got C squared is equal to A squared plus B squared minus 2AB cosine of theta. And the nice thing about this expression, because we can always kind of check it, remember when theta is 90 degrees, cosine of 90 is 0, and that goes away. We just recover the Pythagorean theorem. So now we just have our expression for C, which is going to be our L sub n prime. So cranking this thing out, we get L sub n prime squared is equal to the original new side. So the A squared, doesn't matter which one's which, 213.794 squared plus the vertical length, that's 149.775 squared minus twice AB, 213.794. That's A, the B is 149.775 times, I have to continue this on, times the cosine of that new angle, which is 89.9284. And make sure your calculator button, watch it. So set your calculator button to degrees for this particular case. And we find that L sub n prime, if we do this analysis, is 260.8839. And so now all that's left is to go ahead and do our final calculation. So remember, epsilon n is the original, I beg your pardon, the final L sub n prime minus the original, all divided by the original. So that's going to be 260.8839 minus the original, which is 261.517, all divided by 261.517. I know I'm going a little bit over. I'll owe you a minute or two over the course of the semester. That's not going to happen. And so we see that it's gotten shorter. So we do this and we find, then when we do the conversion, we'll find that the normal strain is negative. We're going to go ahead and do the 10 to the minus 6, negative 2421 microstrain. There we go. Tough problem, but now that you've seen how it's done, you know how to do it. All right, thanks for sticking with me for a few, 45 seconds today. See you next time.